this is one of the things everybody ever worked with a multimeter, like that, comes up with, why didn't I think of this thing? Hey nerds, yeah, I'm really back. This time for real. I'm living in my beautiful apartment in beautiful Gran Canaria. It's 27 degrees outside. It's getting a bit chilly in the evenings. We're going down to 22 something, but well, this is the time of year when it gets cold over here. So, yeah, time for more videos. And yeah, one of the biggest things over here is, you probably heard it over at Tech Channel, the electronics channel we do bi-weekly on Sunday. Yeah, I'm a sponsored people now from PCBWay, yeah. And tell you later about this when we do a bit of PCB ordering for this project. But let me get back to this little project over here. In fact, this is a project I did together with Richard from Non-Electronics Repair, and he came up with the idea because his Fluke does something my not as cheap Unity over here doesn't do. Let me show you. One of these modes you probably always use is continuity. If you never heard of continuity in multimeter, you probably don't own a multimeter. You maybe want to get one. All right, let me switch this thing into continuity. In the display, you see the little bleepy icon over there. So when I now touch both of the ends of the contacts over here, it bleeps and there's a little light coming on. Isn't this fancy? Well, Richard's Fluke does something more. If you contact this with any kind of diode junction, it does a short bleep. It doesn't do a continuous bleep, it does a short one, which is very, very handy when you're trying to figure out what kind of junction do I see here. Is this a schottky? Is this a normal silicon diode? What do I see over here? I have no idea why this isn't included in one of these multimeters over here, because this is simply software. You don't need any fancy change in the hardware of this unit of the system. You simply change the software to something that does this. So we were sitting around with a Tropical, like you do over here in Gran Canaria, and we thought, okay, can we modify a DMM, a multimeter, to do that? And this was our first approach, and I said, sure, we only need a little microcontroller, and we only need a microcontroller and a beeper, of course, because I can use the ADC to get the voltages we see on the test pins over here, and then we can select what we want to do with that. If we see something about, say, 0.3 volts, this is probably schottky something. If we see something around 0.6 volts, we in a normal diode junction. If we see anything higher, it's open or something, nothing happens over there. And if it's below 0.1 volts, we're probably in a short. So we fiddled around with this thing, and what came out is this thing. Yeah, as you saw in the video description, this is Mr. Bleep, as we call it. And it does exactly what I talked about in the intro before. So let me show you, let me demonstrate. Switch this on. Ooh. No explosions, and we see on the little display the current voltage we see on the tips of these test leads here over here. If I do a short circuit, the little voltage drops to 0, and it's a loud beep over here. I don't know how good the microphone is picking this up, but it's freaking loud. And you see there's a green LED coming on telling me, okay, this is continuous, and I stop this now because I'm going deaf over here. Yeah, if you're wondering, this only flickers on camera. If you see it in real time, this is no flickering at all. But it works pretty nice for me. And I got a continuous bleep for this, and I brought us some diodes that are not in shot right now. Wait. And I have no clue what these diodes are. No, I really don't know, because I just cut them from the tape reel. So let's see what I have over here. Wrong direction, of course. There was a short bleep and a blue blink, and I see 0.19 volts on the multimeter display over there on the module. So this is a schottky diode. It's blue, a blue blink. And a other type of bleep. This was a lower type of bleep, and this is a red blink there. And the voltage over there tells me something about 0.58 volts or 0.6 volts. So this is a normal silicon diode. We were testing this out against Richard's Fluke when we tried this initially, and I was sitting on the other desk, and Richard was playing around with this, and he did a short circuit, and I heard 2 bleeps, bleep, bleep, and I thought, okay, this is so slow, we need to make this faster. And he said, no, the slow bleep was a fluke. Dios is so pretty fast. And this is one of the big upsides here. So you get a really, really fast thing over here when you do the... This is really, really fast. The little voltage thing over here is a standard module you can buy as a one thing. And you see it's all powered by a 1.9 volt cell because we wanted to have 5 volts stable here, and you can use anything. We were talking about doing a version with 2032 batteries, but for now we stick with the 9 volt cell. All right, since this is a bit boring and you don't see anything here, let me dive into the electronics. Way better. So here's our little PCB. When I designed this PCB, I was especially looking for beginners over here. So I used large pads. These are always large pads, so it's easy to solder. We don't use any SMD components by design because we wanted to keep this simple for everybody to use this. And since we think this is a tool for beginners. So all the components are through-hole. You can easily fit them in here. We have some big over here, upstanding resistors over here. There's an optional RGB LED. You saw this on the little PCB. This is totally optional. If you don't want to use this because the bleeping thing is a gimmick over here, you simply don't attach a RGB LED and it's fine. Same with the voltage monitor. If you don't have this or you don't want it because you don't need it, you simply don't attach it. This is totally optional. This thing works standalone without the RGB LED and without the voltage monitor. Okay, we saw the PCB. Maybe we should take a peek at the schematics. And the schematics aren't fancy at all because there's not much going on here because most of the thing is a microcontroller that does all the fancy schmancy deciding what voltage level do we have and what beep do we do. We showed this before on Richard's channel, so this is a recap. You maybe want to skip this if you saw this already, or you maybe want to listen to me again explaining this again. Well, let's get in there. As stated before, this all developed around a little microcontroller. I went for an 80Tiny85. This is not an Arduino per se. We program it using the Arduino IDE, but this isn't a official Arduino thing, and the core isn't official Arduino either. So this is a little controller over here. This has a RGB data, so we're using WS2812 thingies. This is an APA 106 in 5 millimeters. So this is a protocol for this. You only need 1 data pin, but it saves me 2 pins. If I had used a real RGB LED, I would have used at least 3 pins, and this way I get away with only 1 pin. There's the analog in, and this is all you need. We're simply dropping the analog in from the parts right into the CPU. This is not protected. If you drop in anything more than 5.5 volts, you fry the CPU. This is by design a bit, but we were talking about doing a complicated protection circuit around the inputs, but we thought, okay, we want to keep this simple, and protection circuit will make this really more difficult to follow, and we were going for, okay, you only want to do this on a circuit that doesn't have power. So this is why we did this way. Yeah, and on the other side, there's a bleeper. All the rest is in the CPU, of course. We go through the software in a minute. Microcontroller connections are these banana jacks, and let me tell you, when I measured these banana jacks down in the beach house where I lived, I didn't have the right calipers, and there was bad lighting, and I screwed up. These banana plugs doesn't fit the footprint over here. So if I would do a revision 1 of these, this is probably the thing I need to change the footprint of. Down below, there's a totally useless RGB LED. There was a long discussion about the LED. I said, come on, let's throw it in there. I have space in the CPU left, so I can program this. And we were going for, okay, you don't need this because you only want to go for the sounds. This is not something where you want to look at. And then somebody said, okay, the RGB LED isn't a bad idea because there are people out there are tone deaf. So they can't distinguish between high beep, low beep. So this is maybe a thing where people can use this tool even if they can't distinguish between the high beep or the low beep. So if you want to have it, it's there. Throw it in there, the code runs anyways, and it doesn't slow down the CPU. So there you have it. The absolute complicated power section over here, yeah. We were going for easy stuff again. We didn't use a no-drop regulator. We want to have something that everybody is lying around and there's no problem to get one. So we went for the trusted 7805. We're using a normal-sized one in a TO220. And we have this tiny one with this looks like a transistor in the TO92 package. I'm better with SMD packages, forgive me that. So you can choose anywhere, this one or this one, it doesn't matter. Please never use both, use only one. Some power LEDs, some caps for the power thing. There's a switch, yeah, I included a switch. I'm very proud of me because normally I forget switches. So you can switch this thing off when you don't need it. Yeah, this is a poor man's current source. The decision to use an LM317 to use as a current source was simply because component counts. This way we get away with one resistor and the LM317, which is a ubiquitous device, and the optional C4. I included this over there. It doesn't hurt the thing, and maybe it makes the output voltage a bit more stable, or the output current a bit more stable. So we're simply using the R3, and if you calculate by the calculation from the datasheet, it just gives us about 1.5 milliamps, which is in fact enough to light up LEDs. And this is a nice feature. Maybe I show this later. I hope I think about this. Well, future dad, remember this. Some more boring stuff, sorry for that. The bleepers over here, you need a passive bleeper, not an active one. Active bleepers, you simply drop on 5 volts and they start to bleep. Passive ones need a frequency on the pin, so we need a passive one because the CPU is generating the frequencies. We dropped in a 22 ohm resistors over here. This is for how loud do you want to have it. If you put the whole shebang in a little box, you maybe need a louder speaker, so you simply bridge over the speaker or you try around. Anything will work over there. The signal from the CPU will get distorted anyways, but the CPU doesn't seem to mind, so looks like we're getting away with this. We had some input filtering over here, but this is what it came down to. We simply get the source and drop it into an analog and we're done. And over here, this is the optional voltage monitor. I can show you this thing at AliExpress. Just a second. Yeah, even on the Canary Islands, you buy your stuff at the Chinese because they're cheap and they work, in contrast to Amazon, that doesn't work over here. So these are the things you saw in the video. You can choose your color about everything you like. You need the 3-line version, the 0 to 100 volts over there, because otherwise they only start measuring at 4 volts and after that they switch off. So you need the 3-line version over here that costs 2 cents more. So yeah, this is really expensive so far. So with shipping, you probably get away with $1, €1, something for the display. Again, if you don't need it, just simply leave it open. The whole shebang will work without this. And you can choose your colors over here. Isn't this fancy? Yeah. So we checked all the hardware now. We know how the thing works. And you probably think, how do I get mine? So let me show you. If you look down in the video description, you find a little link that looks like this thing. Well, I'll simply press return now because you can't see anything. And this brings you over to the P Cloud share, where I stored all the things you need to build one of these little things. And I hear people screaming, why isn't this on GitHub? Or do we need to get this on? I have no clue where you want to store this anyways. Let me tell you this, GitHub for me is way too complicated for stuff I do. I don't need collaboration on this. And this is the way I do this. If you want to have this, this is where you can get it. No GitHub for me. If you look at the file size over here, nearly 240 megabytes, you think, okay, this is a big file for some Gerbers. No, senor. There's more in there. Let me show you. So after downloading and unpacking, I'm imagine that I don't have to show you how to unpack a zip file and download a zip file, right? Right? Okay, you know this already. Perfect. All right, you end up with this thing over here. This is stored on my data drive, and this is Arduino Mr. Bleep YouTube. So this is the whole shebang you need. For once, there are schematics over here, and these are the schematics you just saw on screen in my editor right away. you set up for this one. If you want to find out how did they do this, there are the Gerber files. You need to order your PCBs, which we'll do at the end of this video. Some ODS files where I did some ADC calculations. I left it in there because if you want to have a look around, just play around with this. I already don't remember what I did there, but you maybe want to find this helpful, maybe. And the most important thing, Arduino_Bleep. This, my good sir, is a complete Arduino IDE. In a portable version, I did a video about this. And in the portable version, into the sketchbook folder, you find Mr. Bleep DMM differential. This is the other way we did this. Richard shows this on his channel. And I left you some archives over here with some not finished and test versions and play around things because we had to do a lot of fiddling around. We did a thing where we programmed the microcontroller to do a serial output to show us what it sees on its ADC port, so we can get an idea how we write with our calculations. And this is all in the archives. You don't need this if you only want to build a Mr. Bleep. You don't need this. Go back to Sketchbook, and you only need the Mr. Bleep for the standalone or the Mr. Bleep DMM differential for the differential version Richard showed on his channel. So, want to dive into some code? Let's do this. Oh no, this is Arduino 1.8.19. This is so old. You know what? It works, and I could do the portable things with this. If I have to do this in the 2.0, I have to send you, okay, you need this core, and you need maybe this library, blah, 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 blah. And this way I can simply give you one big thing, and the tools, it's always set. The chip is already set, the clock is already set, everything in here is set. You're ready to go. You simply hook on a programmer. Oh, did I mention that you need a programmer? And you're ready to go. I can't do this in the 2-point-something version, and I keep my project sorted in this way. So bear with me, live with this. Just feel free to port this thing over to Arduino 2.thing. I think the code won't change, but I'm not sure if the core library will work fine under 2-point-something. And for now, for the time being, this is the way to go for me. So after you started the IDE, go to Files and go to Sketchbook, and there you find Mr. Bleep or Mr. Bleep DMM differential. As I said, I won't go into differential because this is mainly the same code, but we use a different way to read the ADCs. We go for the standalone version, and this is this one, the Mr. Bleep over here. So sometimes when I'm feeling fancy, I'll draw in this little chip over here that keeps you an idea which is connected to where, so you don't have to guess this thing. Some more background you guys need to know. When we planned this, we were going for component count. We actually discussed doing an analog version of this, and then we came around and said, okay, we need probably half a PCB for that, and we can all do this in one CPU. When we went for, okay, extreme low component count, we decided to not go for a resistive divider in the input. We simply drop the voltage, we measure it directly into the chip. But this means we have to know the working voltage of the chip. The ADC range changes with the voltage you run the chip with. So if you run it on 5 volts, like on the standalone version, the ADC have different ranges than on a 3.3 volt version. So I did something over here that just runs on 5 volt, and then from there I decide which voltages I use. I define some analog and a bleeper, and this is a time for the bleep. If the time is too short for you, you can extend it over here. This is my low frequency, my high frequency. This is in hertz. So if you want to have different frequencies, you can change them over here. And there are my levels. Define everything below this is a short. So if my ADC measures something below 10, this is a short. Short as in short circuit and not short time thing. The schottkys are defined over here. This is a window, and the normal diodes defined over here. This is always the direct reading from the ADC. If you command this out, this runs on 5 volts just by doing this, just by doing the /forward, these values would be used. You can tell these are different from the values we do on 5 volts. These are higher because the ADC range is spread across about 3 volts and not around 5 volts. I need some global statuses over here. This doesn't work the other way around, so I'll keep with the bleep diode status over here as globals. When we were playing around with the old shebang, we came into the issue of debouncing. These measurement leads, of course, debounce like crazy. So we went around and said, okay, we need to do a bit of a debouncing issue. And this is what this array is for. I tell you more about this when we come to the array later. This is where the neopixel come in, and I tell you more about this over here. So this is more what we need to do here over there. One downside within the neopixel is I need at least 8 megahertz in the CPU clock. So we're wasting energy here because I could run this on 1 megahertz and this would work too, but not with a neopixel. Neopixel needs at least 8 megahertz because it generates something about 800 kilohertz in control values for the little LED. All right, this was more the global setup over here. So now we've all the libraries set up and we're ready to roll. And let's do the usual thing. Let's imagine us being the little CPU and running through the code. So the first thing our little CPU will do is run into setup. So let's see what's happening in there. Of course, we need to set the bleeper to output, and this is all neopixel. So we begin the neopixel thing. We set the pixel to off, and don't forget to use the little show system over here. Yeah, you know, this never happens that you forget to set the show, and then you fiddle around for about half an hour trying to figure out why your damn neopixel doesn't show anything. So always after you set the color, use the little show thing. The array I was talking about because of debouncing is filled up over here with analog in, so I simply read the analog as much times as array size, and this fills up the array. So this is the easiest way to do this with a little for loop. So this is the easy way to do this. So setup's done. Let's see what's happening in the loop. All right, as I said before, we have an array. This is more for doing the debouncy thing. So I'll read the analog into an array. This array currently is 3 values. And this little thing always fits in one of the little slots in the array. So you go 0, 1, 2, 0, 1, 2. This is a nifty way with a modulo operator to do the work, to do the shift around to go back to 0 after you reach the high point. This is array size. And with that, you go 0.1, 0, 1, 2, 0, 1, 2. Yeah, I said this before. From here on, this is pretty easy. I do a is in range, and this is in range function, we can check this out now. Is in range, let's see, this is over here, and you see it takes 2 unsigned 16-bit values, so this is what comes from the ADC. And it runs through our little array, and it asks, are we in range? And it does this as long as this array runs. If one of the values is not in range, one of those, we return a 0 and simply get out of here. If it runs through the whole thing and we never ran into a thing where this is not in range, we never get to this, we return a 1. So we'll be sure if we return a 1, a true, this is in range. All the arrays are in range of these values. So you can imagine if we're in range of diode high until 1023, so 1023, the ADC is a 10-bit value here, so 1023 is 10-bit. The line is open, so we set the pixel color to 0. We don't forget to show, and we do a no tone. You maybe have seen Arduino doing tone things. This is the easiest way to beep the bleeper. This is not nothing fancy, and it's in the core functions already included, so I was, lazy dad, of course. I set all my bleep statuses, these are the global things, to 0, so I know nothing is on. We're totally off here. If we have something in range of something, we do these things. Is in range is the same here, and we declared diode low and diode high, so this is a normal diode, so something in the range of 0.6 volts. Then we do a bleep diode, and I shortly run through these 3 over here because you see they are all the same. So if the values in my array are in the range of diode low or diode high, all of them have to be in this range. And then I do a bleep diode. If they are in the range of schottky low to schottky high, I do a bleep schottky. If they're in the range from 0, nothing, to everything is below this is a short, we do the bleep short. Not short as in short time, just short for short circuit. So this is a whole loop. You can already tell there's room for optimizing. If I would do some optimizing over here, I would do some energy saving. Maybe set the system to sleep for 1 millisecond after the loop was run for one time. But I'm not sure. I have to reinitialize the ADC for that, and if the ADC needs time for that. And yeah, lazy dad, I know. Let's have a peek of one of those bleepy things. So bleep diode and bleep schottky are the same. So we can have a look at this, and this is the same for the other thing. So bleep diode. There's a status. This is the global thing. It's not bleep status. So if it's off, this runs. If we ever come over there. Because if it gets called and this is not on, this runs once. And of course, the status over here gets set too high. So this only runs once. If it sets too high, this will skip this and continue over here. So we set the neopixel to some color. We have to do this. For safety reasons, we do a no tone. I don't want to have some will in there, so I do a no tone here. And then I set the tone to the bleeper as a pen and bleep low frequency just to do the bleep. I set the bleep diode status to high. This is the thing that makes sure that this only runs one. And I use a static variable over here that's called last time and set it to the current millis. So when this thing is run, I'll simply throw in the current millis into last time. So, and now I do a thing you maybe remember from the other things. I do a check how much time has passed. I simply subtract last time that I set over here from the millis. And if this is bigger than the short time bleep in milliseconds, this is a variable that's what's set to 80 milliseconds, I'll do these things over here. I'll set the pixel color to 0, so I switch off the LED. I'll do the little pixel show, and I do a no tone, so I switch off the sound, because I want to have a short bleep. This was actually the most complicated part of the whole code, because I needed a way to switch off the LED, and I needed to do is, if it's shorter than 80 milliseconds, it must be cut off anyway, so this is why all the shutdown codes are existing in the loop. So as you can imagine, bleep diode, bleep schottky is the same. It's the same, but it does a different color and it does a different frequency. But in fact, this is the same. Bleep short actually is easier because it doesn't have to do the check. Oh, am I on for, say, 80 milliseconds or something? This simply keeps on as long as the leads are crossed. And this, my friend, is the whole shebang. This is all the code you need for this. I'll do a short compile run and see how big this gets. So this thing isn't very big. This takes about 3 some by K of RAM, and we have loads of dynamic memory left. So there's option, if you want to modify this code, there's space left. 2 questions remain. How do I program this naked chip? And how do I get my PCB? Let me show you. Well, look at this. Isn't it cute? This is the tiniest program I know to do ATtiny85. On my German channel back in the days, I made a video on how I built this thing, because this is built on a reference design you do for the programmers. Let me know if there's need to do these. If you want to program these, you simply hook them up to USB, drop in the little chip, close the ZIF socket, and you're ready to go. And the programming is done with the Arduino IDE with the settings already did in the Arduino IDE. If there's need to build one of those, please let me know in the comments. So you have everything ready. You have the CPU programmed. You're ready to solder everything onto the board. But of course, you need the board for this. So where do you go? Of course, you go to PCBWay. And I'm not stealing here. All right. Hit the nice orange quote now button. And don't start looking around over here. Just simply go for quick order PCBs. There you want to add your Gerber file over here. So just click Add Gerber. This is the Gerber you find in the zip archive. Upload it. And there you go. There's Mr. Bleep. There's a PCB for that. You're ready to go now. Well, you can have some settings over here. I normally go for a bit thinner PCB. I normally find with 1 mil PCBs. I don't need 1.6 mil. This is not really useful. And I'm usually going for, of course, black PCBs. Of course. One thing you may have an eye on is your shipping costs. You see the shipping costs over here to Spain with the global standard is 390. So over here you can choose your land of origin. So if you live in the United States, you simply go for United States, and then you can choose one of those, deliver over here, and you see there's a huge price difference, but there's also a huge time difference. If you go for something like AliExpress, this normally arrives in 2 to 3 weeks, but it's way cheaper to use this than, say, DHL. This all depends on how fast you need your PCBs. This is a turnaround question here. If you find with 19 euros for DHL or DHL with already paid taxes, so you maybe want to use this. If you find with waiting some, maybe use a cheaper supplier over here. This is with 4 euros, 5 euros for the PCBs, 4 euros for the shipping. You get them under 10 euros. So this is a no-brainer. So this is the software and schematic side of the Mr. Bleep project. Head over to Richard in the video. This is linked in the description to see the use case for this. Richard is way better with all the use cases, and he can show you way more. I simply forgot about the LEDs, but Richard will probably show this in his videos. So head over there to get the whole story and have fun with Richard's videos. He's a very entertaining man. If you don't know him, everybody knows Richard, oder? Right? All right. This is it for me for today. I hope you enjoyed the video, and thanks again for PCBWay for sponsoring this video. And yeah, this is a great cooperation. Expect more to come around this, and expect more strange projects in the future coming up. We have some in the pipe. Well, if you have time on Sunday evenings, just have a look at the electronics channel, link in the description, of course. We'll be there on Sunday evenings, so Carlos, Richard, and me, and having fun. This started as an electronics channel, but for right now, this more feels like comedy and explosions. This is a simple way for us to chat with you people. So please feel invited. Come around, chat with us in the YouTube chat, and have fun there. I see you guys in the next video. Bye!